Okay, guys, now having refreshed myself with a nice cup of coffee, let's dive into Proton NMR spectroscopy. First thing you will notice is in the example spectrum, it's far more complicated looking than the carbon-13. Carbon-13 had single peaks. That was pretty easy. These peaks are being split. Why is that? Well, let's have a little think about it. Hydrogen 1 makes up 99.9% or more of natural hydrogen. Carbon-13 only makes up 1% of natural carbon. So, effectively, the electron shielding in carbon-13 is a lot less than the electron shielding in hydrogen 1 because clearly there's a lot more of them. What that means is, in carbon-13, the magnetic field of one nucleus and the shielding around it is not felt by the nucleus next door because it's too weak. That is not the case with hydrogen. In the case of hydrogen 1, the electron shielding is much, much greater. You're going to see immediately, look at these chemical shifts. 1, 2, 3, 4. Carbon went down 200 plus. So the electron shielding here is much greater. Therefore, there's not such a big difference between these values and the TMS value. But not only that, the electron shielding of one hydrogen can actually be felt by the hydrogen next door. And that causes a splitting of the peaks, as we're going to see. Okay, so again, they're reminding us that it has to be hydrogen 1. We could use tritium, but tritium makes up a ridiculously small amount of hydrogen. So why go with something like that when hydrogen 1 clearly is the more popular isotope? Now, in an NMR spectrometer, we haven't actually talked about the details of what's done, but we put the sample in, we dissolve it basically in a solvent, and then that sample is placed into the machine and it's spun to give a kind of a consistent environment. And don't worry too much about that. But basically, we cannot use any solvent that contains hydrogen because the solvent would then be producing peaks in the NMR, in the proton NMR spectrum. And we don't want that. We want our sample to be the only source of the protons. So those are some of the solvents that are used. Depending on what you're using, if you're using a non-polar material, then you'd go for something pretty much like this, which is very non-polar. And if you're going for something more polar, you'd go for this solvent here. Okay, now as we saw in the earlier slides, each of those hydrogens there, the 3 on the left, will produce one peak. The 2 in the middle will produce a different peak or signal, and the green one, a third one. Okay, now the first thing I have to say, this slide is going to cause you confusion. Basically, if you were to look up the Proton NMR spectrum of ethanol in Google Images or whatever, you would find this spectrum there, but you would also find others with this peak over here. And that's where I want you to actually imagine it is. Because effectively, this peak here is being caused by this green hydrogen, which is clearly attached to an oxygen. Therefore, will be de-shielded, the electrons will be drawn away from it, and therefore will appear further downfield. The reason it appears there is due to complicating factors like hydrogen bonding and things like that, which we do not need to know about. So again, I want you to imagine this peak is for those hydrogens there. They are furthest away from the oxygen, so they are shifted the least. This peak are these here. They will be shifted the next amount, if you like, because they're closer to the oxygen. And this one, which is attached to the oxygen, is over here, not there. Okay, got that? Good. Don't worry about the splitting just yet. Okay, now The splitting depends on the number of adjacent hydrogens. If you want this explained in more detail, that can happen, but you don't need it. And what we're going to do basically is keep it simple. And what we're going to say is that it's not actually telling us about the splitting yet. What it's saying is the chemical shift is much smaller, which is what we said earlier. And that's basically because the percentage of hydrogens is much, much greater. Therefore, the shielding by their electrons is much, much greater. And therefore, there's a very, very slight difference between the TMS peak, which is at 0, and these peaks, which are just 1 or 4 parts per million. Think about it. These are parts per million. So the magnetic field, for example, felt by these hydrogens here is just over 1 part per million less than the magnetic field felt by the hydrogens in TMS. Okay? But that 1 part per million can be picked up. That's how sensitive this machine is. Okay, first of all, then it's just going to ask us some questions about chemical shifts before it goes into the splitting patterns. Okay, so which compound would give that spectrum there? It's just got the 1 peak, meaning the hydrogens must be in an identical environment. Okay, so let's have a look. Now get carbons out of your mind now. Don't say, oh, those are the same. We're looking at hydrogens. These 4 are identical. Those are different. That would produce 2 peaks. This one was our example a moment ago. 1, 2, 3 peaks. This one is our answer because those 3 and those 3 are in exactly the same environment. Those 6 hydrogens would produce the single peak. Okay, this one, not easy to see this. This is actually producing 2 peaks. Again, remember, don't think there's 3 peaks or what's going on here and treat those as 2. This is basically a single signal which is being split. And this is another signal which, as you can see there and there, is also being split. So what we're looking for here, guys, is 2 different environments. Okay, so let's look at the first one. There's 1 environment, 2, 3, 4. Let's look at this one. Oh, actually, let's look at this one first. 1, 2, 3 different environments. Here's our answer. This nitrogen is attached to an ethyl group on 3 sides. So those hydrogens, the ones nearest the nitrogen, would give 1 peak. And then those 9 further away would give the second peak. Okay? 3 peaks, 3 different environments. Which one are we going for? Okay. Here is our answer. 1, 2, 3 different environments. 2 different environments. Okay. Here's our answer. The ones nearest the oxygen will give 1, those 4, and the 6 on the outside will give the other one. And finally, there's a peak there. It's quite a long way away. I mean, what is that, about 8, 10, that's probably 11 point something units. That's probably about as big a chemical shift as a proton NMR will ever give. So that hydrogen there must be pretty well de-shielded from the magnetic field. Okay, well, we've seen the OH one earlier. It wasn't as far down as that, but look at that hydrogen. Now, it's got, sorry, I should be talking just about different environments, but think about the fact that that hydrogen there is attached to an oxygen, and right next door is a carbon oxygen, which will also draw electrons away from it. So that hydrogen there is very well unprotected, if you like, or whichever one you want to say, de-shielded by the magnetic field. Incidentally, all we had to say was there's two different environments, and there's your answer there. Okay, this one has 3 environments and this one has 1. Sorry guys, jumping the gun a bit, but it's all good stuff. Okay, there we are. It's telling us now about areas under the curves, okay, which we said earlier. Now this is difficult to do when the peaks are split like this. And what would happen is, if you were given this question in the exam, we would give you those numbers. So we would tell you 3 hydrogens, 1 hydrogen, 2 hydrogens, or 6, 2, 4. These could be like an empirical formula. These could be the simplest ratio, but you'll find they're very, very easy to recognize. All right, it's called integration, and those numbers are what come out of this integration. Okay, now we're going on to the splitting. Let's have a little look at this one here. Okay, so what we are basically facing is here that we know about, obviously, the external field causing the nucleus to flip against it. Now what it's saying basically is, if there's a hydrogen next door, then effectively it can either be lined up with the field or against it. So the hydrogen that you're measuring is being affected by that hydrogen's field next door, which could be one of 2 fields. Therefore, it will be split into 2 peaks. Don't worry too much if you didn't understand that. That's quite tricky. There's a simple rule coming up, and that's all you've got to be able to be able to do. Okay, so it's called spin coupling, and it results in splitting. The amount of splitting depends on the number of adjacent hydrogens, and it's simple as this. If there's 1 adjacent hydrogen, the peak is split into 2. If there's 2 adjacent hydrogens, it's split into 3. If it's 3 adjacent hydrogens, it's split into 4. It's called the n+1 rule. So you just simply look at how many adjacent hydrogens are present, and then the peak next door, or the signal next door, is split into 1 more than that number of hydrogens. Now, I will certainly be going through the reasons for this and the relative ratios of the peak heights, so don't worry too much about it. I'll be going through this in class with you. But if you don't understand it, don't worry, you will not be tested on it. As long as you remember what we just said about this n+1 rule, that's all you need to know, okay? So in this particular one here, those have been split into 2. That means there was 1 hydrogen next door. This peak here has been split into 3. That means there were 2 hydrogens next door. Okay, next door means on the carbon next to them. So if you look at this molecule here now, okay, we can see that the hydrogens in blue are identical, and then this hydrogen is different. So this is obviously going to produce 2 signals. There they are. But which one is which? Well, from what I've just said, hopefully you will realize that these 2 blue ones are being split by this 1 into 2. Therefore, it's going to be that peak. This hydrogen, on the other hand, is being split by 2 hydrogens. Therefore, this peak will be split into 3 and give us that one. Okay? Also, you'll notice there are 2 chlorines attached to this carbon, 1 attached to that one. So you'd expect this hydrogen to be further downfield anyway, so it's working beautifully. Okay? They call these peaks, by the way, doublets, triplets, quartets, quintets, and so on. Okay, now all the stuff in the yellow box is basically saying what I've just been saying. So please read what's in that box when you're going through this for yourself. Okay, the hydrogen in red then obviously is split into a triplet, as we've just said. Okay, in this particular molecule here, there are 3 adjacent hydrogens, three hydrogens on the carbon next door. Therefore, it's split into 4, which of course is called a quartet. So let's see if we can now do a little bit of checking. So the hydrogen in red there, it'll be split into what? Hopefully, you said quartet. There's 8 of these, plenty of practice coming. Okay, now then, something you have not been told yet is this. If a hydrogen is attached to an atom other than carbon, it'll only be oxygen or nitrogen. Then basically it doesn't get split at all. Neither does it cause any splitting. So just remember this one here now, because it's attached to an oxygen, is not affected by those hydrogens, and therefore will be a singlet. And you may remember the ethanol spectrum we saw at the start, it was a singlet. If not, go back and check. Okay, what about this hydrogen, the one in red here? Now this is going to introduce you to something a little bit different. For example, you might say, right, okay, so this hydrogen has 3 hydrogens there and another 3 there. That's a total of 6 hydrogens. Therefore, this pq would be split into 7. 7 would be called a septet, but it's not there. And the reason it's not there is because that doesn't happen. You see, these hydrogens here are identical to those hydrogens there, so they act as 1. So effectively, it's been split into 4 by the adjacent 3 hydrogens. Got it, guys? Make sense? Okay, what about that hydrogen there? Now you might say, well, what about the other 2 hydrogens? They're identical, so it could have chosen any of those 3. The point is there are no hydrogens next door, and therefore it's a singlet. Okay, what about this one here? Well, obviously there are 2 hydrogens on the neighboring carbon, so this will be split into 3. What about this hydrogen here? Now then, is it going to be split by the 2 hydrogens on the carbon next door? Or just the 1? Remember, a hydrogen attached to an oxygen does not get split, neither does it cause splitting. So the single hydrogen there will split that into a doublet. Okay, the hydrogen here in red. Are there any hydrogens next door? No, so it's a singlet. And what about these hydrogens here? Well, this hydrogen is attached to a nitrogen. And as we know, once it's attached to an atom other than carbon, it's a singlet. Okay, guys, I'm going to take another break here because I need another cup of coffee.